Hello guys, welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course on states of matter, and I hope you are enjoying this course with me. So today we begin with lecture 24 from the course, but make sure you watch the previous ones before viewing this one. In the last lecture, we learned about the kinetic gas equation, and before that, we learned about the kinetic molecular theory of gases. And while we were talking about the kinetic theory, well, what I told you was that all the gas laws, they were experimental laws. All the scientists, they had done various experiments to give us the gas laws, for which there was a reasoning required why all those things are happening. So the kinetic molecular theory of gases, this was the theory that gave us an inside story, the story of the molecules they are behaving in the gases to give us the various relations as we saw for the various gas laws. So today in this lecture, what we will be doing is we will be developing an understanding how the gas laws they can be explained by the kinetic theory of gases, and then once we have done that, we will be talking about another very important topic, that is going to be the different types of velocities. While we were discussing the kinetic gas equation, we talked about the average velocity and the root mean square velocity, if you remember. So we will be discussing more about these two types of velocities, and one more type of velocity we will be discussing here, that is going to be the most probable velocity. So let us begin with the gas laws. So the first gas law that we studied was the Boyles Law, right? And now we are going to explain the Boyles Law according to the kinetic molecular theory of gases. So according to the KTG, what we have is, as the pressure exerted by a gas is because of the bombardment of the gas molecules or the collision of the gas molecules on the walls of the container. So what this means is that the pressure, this is going to be proportional to the number of collisions per unit area per second, right? So I hope this is all clear to you. And then what we have, a chief requirement for the Boyles law is that we should have constant temperature, right? So at constant temperature, now what is going to happen? At constant temperature, the average number of collisions is going to remain the same, and the average speed of the molecules is going to remain the same. Right? What you have studied is that the kinetic energy of the gas molecules is directly proportional to temperature. This is what you learned in the last lecture. So if the temperature is not changing, then the kinetic energy of the gas molecules is not changing. The speed of the gas molecules is not changing. And when I'm talking about the speed, it is the average speed, right? So because due to the collisions, there is going to be a change in speed of the molecules, but the average speed is going to remain the same. And hence the number of collisions, if we are talking about average number of collisions, that is going to remain the same. So now what we are going to do is we are going to increase the volume. Okay. So supposedly if this was the container, right? So this was the container, and let us assume that this wall, there is going to be 10 collisions. Okay. 10 collisions taking place on this wall of the container. Fine. Now what we have done is that we have increase the volume. Okay, so this was the initial volume, so this was the area of this wall as well. Now we have increased the area, but the number of collisions is the same because we did not change the temperature. So this is again the same number of collisions but on a larger area. When this is going to be larger, then what is going to be happening? Well, it is going to be less number of collisions per unit area, and when there is going to be less number of collisions per unit area, well, it is going to be a lesser pressure that is going to be exerted. So what this means is that because of increase in pressure, increase in volume, the pressure has decreased. So V is inversely proportional to P, and that is what the Boyles law say. When we have a fixed amount of gas we have taken in a container at constant temperature, if we increase the volume, the pressure is going to decrease, and if we decrease the volume, then it is going to be more number of collisions per unit area and hence a higher pressure. Fine. Now the Boyle's law, this can be also derived from the kinetic gas equation as well. So what we know is that P is inversely proportional to V, and according to the kinetic gas equation, what we have is PV is equal to 1 by 3 mnu square. Okay, so P is pressure, V is volume, m is the mass of one molecule of gas, n is the number of molecules, and u is going to be the root mean square velocity. Fine, and you have multiplied now this by 2 and divided by 2, so you get PV equal to 2 by 3 kinetic energy. And what we know is that, as already I was talking to you about, that we've discussed in the last lecture, that kinetic energy is proportional to temperature. So what this means is that if PV is equal to 2 by 3 kinetic energy and kinetic energy is proportional to temperature, so PV is also going to be proportional to temperature. Right? So what this means is that if the temperature is constant, temperature is not changing, then PV is going to be constant, or V is going to be inversely proportional to P, or P is going to be inversely proportional to V. So what this means? Well, we have proved the Boyle's law from the kinetic molecular theory of gases and the kinetic gas equation. Next, after the Boyle's law, we have the Charles law. And I hope you all remember what else the Charles law says. It says that for a fixed amount of gas at constant pressure, the volume of the gas is going to be directly proportional to its absolute temperature. So now let us see how, according to the kinetic molecular theory, we are going to explain this. So from the kinetic theory, we have that the kinetic energy of the molecules, this is going to be equal to half mu square. And also now you know that the kinetic energy is going to be directly proportional to temperature, right? So what this means is that if we are going to increase the temperature, the kinetic energy is going to increase, and if the kinetic energy increases, well, the velocity of the gas molecules is going to increase, and the molecules, they are going to start moving more randomly and more vigorously, and this is going to cause more collisions per unit area. And when there is going to be more collisions per unit area, what is going to increase? Well, the pressure is going to increase. But now for the Charles law, what do we have as the condition? That the pressure should remain constant. So if we want to keep the pressure constant, what we will have to keep constant is the number of collisions per unit area. So what we are going to do? Well, to keep the pressure constant or the number of collisions the same per unit area, we are going to increase the volume. So what do we get? We get that with the increase in temperature, there is an increase in volume. So next what we can do is we can try the opposite way. We can decrease the temperature. If there is going to be a decrease in temperature, the kinetic energy of the gas molecules will decrease. Similarly, just like the increase in kinetic energy caused an increase in pressure, now a decrease in kinetic energy is going to cause a decrease in pressure. But we want to keep the pressure constant. So for keeping the pressure constant, we are going to decrease the volume. Thus, the volume is going to decrease with a decrease in temperature, and what we can say is that the volume of a gas is going to be directly proportional to temperature at a constant pressure. Now, similarly, we can also express the Charles law from the kinetic gas equation as well. So let us see how we are going to do that. Well, we already know that the kinetic gas equation is PV equal to 1 by 3 mnu square, right? So you are going to multiply and divide by 2, and what you will be getting is that PV is equal to 2 by 3 kinetic energy. So this is all that we have learned in the previous lecture once again. Fine. So kinetic energy, we also know that this is directly proportional to temperature. So what we can say is that PV is going to be directly proportional to temperature. But for the Charles law, we are going to keep the pressure constant. So when we have the pressure constant, what we can say is that it is going to be the volume that is going to be directly proportional to temperature. And this is what do we have as? Well, this is the Charles law. So we have the Charles law being explained by the kinetic molecular theory of gases as well as the kinetic gas equation. The next law I will be talking about is the Dalton's law. Well, I've left behind the Gay-Lussac law and the Avogadro's law, and I would like you all to try that yourself, just similar to the Boyles law and the Charles law. Now, what we have as the Dalton's law is that if we have a mixture of gases, then the total pressure which is going to be exerted by all the gases, this is going to be equal to the sum of the partial pressures of the individual gases. Right? So let us see how we are going to explain this on the basis of KTG now. So according to the kinetic theory, what we have is that the attractive forces between the gas molecules, this is negligible. Why is it negligible? Because there are large spaces separating the gas molecules, and therefore the gas molecules, they are going to behave independent of one another. They are so away from each other, not influenced by each other. So it does not matter to them whether the other molecules, they are present or not. So average number of collisions is not going to be affected even if more than one gases, they are present as a mixture. Either it is one gas present or it is more than one gas present, it is not going to be affecting any of the gas molecules, right? So the average number of collisions will not be affected if there is a mixture of gases. So the partial pressure due to one gas is going to be because of its own molecules only. And therefore the total pressure which is going to be exerted by the gaseous mixture is going to be due to the impact of the molecules of all the gases on the wall of the container, and hence the total pressure will be equal to the partial pressure of the various gases present in the mixture, right? So I hope it is clear to you that there are no attractive forces, so the gas molecules, they are not influenced by each other, and each gas is going to behave in its own individual way. Fine. So similarly, now let us explain the Dalton's law from the kinetic gas equation now. So what we have is that PV is equal to 1 by 3 mnu square. I hope now you all are going to remember this. And when you are going to multiply and divide it by 2, you are going to get this equal to 2 by 3 kinetic energy, or we can say that the kinetic energy is going to be equal to 3 by 2 of PV. For multiple gases in a mixture, the kinetic energy of one gas molecule is going to be equal to 3 by 2 P1, the pressure exerted by this gas, into the volume, because each of the gas is going to occupy the whole volume that is available to them. Similarly, for the next gas E2, the kinetic energy is going to be equal to P2 into V, and P2 is going to be the partial pressure which is going to be exerted by gas 2. Similarly, for gas 3, the kinetic energy is going to be equal to P3 into V. Now the total kinetic energy is going to be equal to E1 plus E2 plus E3, which is going to be equal to 3 by 2 P1 into V plus 3 by 2 into P2 into V plus 3 by 2 P3 into V, and so on if they are going to be n number of gases, right? So what we have is that 3 by 2 PV, which is the total kinetic energy, is going to be equal to 3 by 2 V, taking these as common and multiplied by the sum of P1, P2, P3 and so on. So what do we get? Cancelling out 3 by 2 3 by 2 V on both the sides, we will be getting P, the total pressure exerted by the gas, to be equal to P1, P2 plus P3 and so on, right? So I hope this is clear that the total pressure exerted by a mixture of gases is going to be equal to the sum of the partial pressures of various gases present in the mixture. And we have explained this on the basis of the kinetic molecular theory and the kinetic gas equation. The next we have is the Graham's law. So quickly let us revise this also. I hope you are enjoying this. We are revising everything with this lecture. So we have the Graham's law saying that if we have constant temperature and pressure conditions, then the rate of diffusion or effusion of the gas, this is going to be inversely proportional to the under root of density. So let us see from the kinetic theory how we are going to explain this. Well, what we have is that the temperature is the same. So the average kinetic energy of the gas molecules, this is going to remain the same. And if the temperature is constant, then the gas with a lower molar mass, this has higher speed. How do we explain this? I hope you can all understand that if we have a thin child and a fat child who are running the race, who is going to win the race? Well, it is going to be the thin child, because he'll be able to quickly run that race, he has a higher speed. So similarly, the gas with a lower molar mass, this is going to have a higher speed, and when it has a higher speed, well, it is going to be able to diffuse or diffuse faster. Now, how do we explain or derive the Graham's law of diffusion from the kinetic gas equation? Let us see that also. So we have PV equal to 1 by 3 mnu square, and where m is going to be the mass of each gas molecule and n is the number of gas molecules. So what this means is that if we are multiplying these, what are we getting? We are getting the total mass of the gas. So let us represent this by the capital M. So what we have is now U square is going to be equal to 3 PV by M, right? 3 gone this side, M gone down. So we have U square is equal to 3 PV by M. Now if you bring V below, what you will be getting is 3P by MYV. Mass of the gas divided by volume. What is that? Well, this is the density of the gas. So we can write that U square is going to be equal to 3 PV by rho. And therefore, what we can say is that U, the gas molecule speed, is going to be equal to under root of 3P by rho. Now, for the Graham's law, one condition was that the temperature should be the same, and the other condition is that the pressure condition should be the same. So, therefore, what we have is at constant pressure, the speed of the gas molecules is going to be inversely proportional to the under root of density. And if we have the rate of diffusion to be expressed R, then this rate of diffusion is going to be proportional to the speed of the gas molecules. More is going to be the speed, more is going to be the rate of diffusion, less is going to be the speed, less is going to be the rate of diffusion. So hence what we can say is that R therefore is going to be inversely proportional to the under root of density of the gas, and this is what we have as the expression for the Graham's law of diffusion. Fine. I hope all these laws, they are clear to you, how we explain them with the help of the kinetic theory and how we can derive all of these laws from the kinetic gas equation. The next topic we discuss today is going to be the different types of velocities the gas molecules they can have. And why is this knowledge important for us? This is important because the gas particles, they are in constant random zigzag motion, and it is their motion which is going to be a guide to the energy which is going to be possessed by the gas as a whole. Now, when we talk about the different types of velocities, we will be learning three types of velocities. The first two you have already learned. Which are these two? Well, while we were talking about the kinetic gas equation, we learnt about the root mean square velocity as well as the average velocity of the gas molecules. So we will be just giving a quick recap to what you have learned previously in the last lecture, and then I'm going to add some information there for you which is going to be important for your examination. And then one more type of velocity we will be talking about today, that is going to be the most probable velocity. So first of all, the root mean square velocity. So this is represented by URMS, and I hope you all remember that it is the square root of the average of the squares of different velocities of the gas molecules, right? So if you want to remember this, what is going to be the root mean square velocity? It is going to be very simple, that you have to first of all take the velocities, right? Then you have to square those velocities. Let us look at the formula as well. So we have the velocities of the gas molecules, all individual gas molecules, right? Then we are squaring those velocities, V1 square, V2 square, V plus V3 square, and then we want to take their mean. How we are going to take their mean? Well, we are going to add all these terms, right? And whatever is the number of these terms, supposedly these are n number of molecules, so we will be dividing this by n, and then we will be taking their root. I think this is very easy now to remember what is root mean square velocity. The square of the velocities, take the mean of those and then put it under the root, and you are going to get the root mean square velocity. Now, if they are going to be different molecules, of gas which are possessing different velocities in such a way that there are n1 number of molecules possessing v1 velocity, n2 number of molecules possessing v2 velocity, and so on, you can just modify the formula to be n1 v1 square plus n2 v2 square plus n3 v3 square, and so on. Add all these terms divided by n, because still the number of molecules is going to be n, and put that under the root, and you are going to get this as URMS. Fine. Now one more thing that you have to remember now is that this URMS, this is equal to under root of 3 RT by M, which is going to be equal to under root of 3 PV by M, and this is going to be equal to under root of 3 P by rho. And this is one derivation that it is very easy for you to understand because we've already done the kinetic gas equation. So let us look at that as well so that you can remember this relation. Okay, it is not going to be asked in the examination to derive the formula or the relationship between all these and the root mean square velocity, but because it is going to be helpful for your understanding, let us quickly do that. We've already done the kinetic gas equation. So the kinetic gas equation you all know by heart now, that it is equal to PV equal to 1 by 3 mnu RMS square. And what is P, what is V, you all know now, right? And now if we have 1 mole of a gas, you also know that multiplying the mass of the gas into n number of molecules, which is now going to be the Avogadro's constant, this is going to give us the molar mass of the gas. So we can replace the equation PV equal to 1 by 3 mnu RMS square to be equal to now 1 by 3 mu RMS square. Right, and we also know that the ideal gas equation for 1 mole of a gas is equal to PV equal to RT, and therefore now we can write RT going to be equal to 1 by 3 capital M, that is the molar mass of the gas, multiplied by the root mean square velocity square. So from here you can derive the value for URMS to be equal to under root of 3 RT by M. And what is R, that is important over here? It is the universal constant, but here we are taking the values of velocity, and it is going to be generally taken to be meters per second in the SI unit. So the value of the R universal gas constant also has to be in the SI units, right? So we will be taking the value of R to be 8.314 joule per Kelvin mole. Please do remember this. You have to understand where you are going to take what values of R. When you're talking about the SI units, you have to take this value. Fine? Okay, and M is obviously the molar mass of the gas, but here again when we are talking about the SI units, the molar mass of the gas is also going to be expressed in kilograms. Okay, generally what we take as the molar mass of the gas is going to be equal in grams, right? But now because you are taking SI units, here the molar mass also has to be expressed in kilograms. Fine. So supposedly you have oxygen as the gas, the molar mass is 32 grams. So here you will not be putting the value to be 32. You have to put it as 32 into 10 power minus 3. This is some mistakes that generally the students do commit. So please do remember what you have to take the value of R and what you have to take the value of molar mass. It has to be in kg. Okay. Now RT you can also write as PV, so we can write this as 3 PV by M under the root. And also you know that M by V, if you put this V down, we just now see that while we were talking about the Daltons law as well. So it is going to be equal to M by V, and this you can represent as the density of the gas. So here we have the relationship for URMS to be equal to under root of 3 RT by M, which is equal to under root of 3 PV by M, which is equal to under root of 3 P by rho, which I told you on the previous slide. How we have derived it, and I think it is very simple. You all know this very well now. So the next velocity term that we having is the average velocity. And this is something that you've already again learned while we talked about the kinetic gas equation. This was the first slide of the last lecture, right? So what is average velocity? Well, this is going to be the arithmetic mean of the different velocities of the various molecules present in the given sample of gas, and we are going to find it out as summing up all the different velocities of the gas divided by the n number of molecules to get the average velocity. Perfectly fine, I hope. So now if we have different molecules of the gas possessing different velocities in such a way that n1 number of molecules they possess velocity v1, n2 number of molecules possessing velocity v2, and so on, then we can just modify the formula to write an easier way of calculation that is going to be equal to n1 v1 plus n2 v2, so on. This is going to be sum up all of these and then divided by the n number of molecules to get the average velocity. Now, what you did not learn in the last lecture was that this average velocity that can be found out to be equal to under root of 8 RT by pi into the molar mass. Okay, and the derivation of this is not in your curriculum, so we will be not seeing how we are going to derive this. You just have to remember this, okay, and this is going to be important, so please do remember this. Many questions they do come related to these values of the different velocities in terms of RT by M. Okay, so you've already learned that root mean square velocity, that is equal to under root 3 RT by M. So now we have learned that the average velocity is going to be under root of 8 RT by pi into M. The next we have is the most probable velocity. So you all have studied in class 10th about probability. What does probability mean? What is that? The supposedly if we have a bowl and in that we have put up some beads of red and white in color, and you are going to pick up just closing your eyes, what is going to be the probability of taking out the red balls, what is the probability of taking out the white balls, and what is the probability of taking both one red and one white, and so on. So many questions you have already done while we were in class 10. So now we have now the most probable velocity. Okay, so most probable velocity is going to be the velocity which is going to be possessed by the maximum fraction of the molecules of a gas. There are going to be many molecules of a gas. Some may be possessing very low velocity, some may be possessing very high velocity. What we want is the velocity which is going to be possessed by the maximum fraction molecules of a gas. Okay, so if supposedly there are 100 molecules and we say that there is one particular velocity which is being had by say around 50 or 60 molecules, so that is going to be the most probable velocity, the maximum fraction of molecules which have that velocity. It may not be the maximum velocity, it is going to be the velocity which is going to be possessed by the maximum number of molecules, and at a particular temperature the velocity which is going to be the most probable for the molecules is going to be equal to under root of 2 RT by M. Again, this derivation is not in your curriculum. How we get this, you have to just remember this result. Okay, so I hope you have now understood what are the three different types of velocities. So now let us look at a relationship between all these three. So to find out the relationship between the three different velocities, let us write out the values for these. URMS, we found out that this is equal to under root of 3 RT by M. Also, we've learned out that U average is going to be equal to under root of 8 RT by pi into M, and UMP, that is the most probable velocity, this is going to be equal to under root of 2 RT by M. So if we want to find out the relationship, we will be finding out a ratio between these three, sorry, and then we will be getting what? We will be seeing that RT by M terms, these are going to cancel out because they are present in all of them. So we will be getting the ratio between the root mean square velocity to u average to UMP to be equal to under root of 3 is to under root of 8 by pi is to under root of 2. From this, we can find out a relationship between the average velocity to root mean square velocity. Average velocity is going to be equal to under root of 8 by 3 pi into root mean square velocity. This is going to come up to 0.9213 into URMS. Okay, so U average is going to be 0.9213 into URMS, whereas the most probable velocity, this is going to be equal to under root of 2 by 3 into URMS, and if you're going to solve this, you will be getting this value to be equal to 0.8164 into URMS. So what this means is that URMS is going to be the maximum velocity, then we will be having the average velocity, and then we will be having the most probable velocity, right? So maximum, if this is going to be 1, it is going to be 0.9213, and if this is 1, it is going to be 0.8164. So 1 is going to be larger than 0.9213, this is going to be larger than 0.8164, and this is the relation you have. This is going to be very important. An easy way you can remember this is that we have 3 velocities, okay, and the average velocity is going to be in between these two. Okay, this is a way to remember it, that this is going to be in between these two, and if RMS is going to be the largest velocity, well, this is going to be the smallest one. So this is how you can remember the order as well. And if you want to find out exactly what is going to be the ratio between these three, what you will be finding out is that UMP to U average to URMS is going to be equal to 1 is to 1.128 is to 1.224. Okay, so these are the values. If you can remember, it is going to be very good. It can be just helping you in your numericals that you will be able to do in a fraction of a second. Otherwise, if you remember this relation, whatever question that is going to come, you will be definitely able to handle that. So that would be all for this lecture, and the next lecture is going to be again a very important one, where we would be talking about the Maxwell-Boltzmann distribution of speeds, a very important topic for your examination. So please be with me for the next lecture, and for that, if you've not subscribed to our channel till now, please do that, and also click on the bell icon so that you get the notification the moment we put up the next lecture for you. So see you again. Have a nice day and God bless you.